SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied. Today we shall discuss about the carburetor. We have seen that in the context of SI engine operation, carburetor is an important element, and though we did not discuss in detail, but the objective of providing this particular element is to supply homogeneous mixture of fuel and air. So, though it is not possible to discuss this particular element in a greater detail, but still we shall briefly touch upon important aspects of this particular element while we are discussing the SI engine operation. So, if we recall, in the last two classes we have discussed the classification of internal combustion engines, and we could classify internal combustion engines based on the number of strokes and types of combustion. These two are the important classifications, while internal combustion engine can also be classified based on the cylinder arrangement. See, we have seen in the nomenclature of both SI and CI engines, piston is having a reciprocating movement inside the cylinder between two locations, that is the between two centers, to be precise, top dead center and bottom dead center. Now, when the piston is having or travelling between these two centers inside the cylinder, depending on the requirement, we need to have multi cylinder engines, and if we need to have multiple cylinders, then arrangement of cylinder can be a criterion to classify internal combustion engines. So, today we shall discuss about, before going to discuss the carburetor, let us discuss about the classification of IC engine, and this is based on the cylinder arrangements. So, the most common type is number 1, most common type is the inline arrangement. Inline arrangement, or that is like this particular arrangement, and so this is, you can see there are 3 cylinders which are connected to one common crankshaft, and this is called inline arrangement and cylinder placed in a line. So, that means all cylinders are placed in a line. So, this is the cross sectional view. If we try to draw another view, it will look like this. So, this is the common shaft, and this 1, 2 and 3, these are the engines, these are the cylinders. So, you can understand all cylinders are connected to a common shaft and power is supplied to this common shaft. So, this is most common type inline arrangement. Next, number 2 is opposed cylinder type. This particular classification is based on the criterion of engine cylinder arrangement, provided if the engine is or is having multiple cylinders. So, this is opposed cylinder type. So, this is opposed cylinder type, that means these 2 cylinders are opposing each other, and you can see there is one even common crankshaft. So, one common crankshaft. So, there is one common crankshaft, and this is opposed cylinder type. Next, we can write next type is opposed piston type. And So, this is spark plug, say this is the spark plug. If this is not this SI engine, instead of spark plug we will be having fuel nozzle. So, this is basically opposed pistons type. You can see that these two pistons are having opposite movement, and the specific feature of this particular type is both are executing power and exhaust stroke at same time, right, but we have two crankshaft. So, for this particular we have two crankshafts, and last one is radial engines. Okay. And if we try to draw the schematic, and so say this is the crank and this is the crank, and all these are we will be having so this is basically see you can see all cylinders are placed along the periphery of a circle having equal radius, and this all cylinders are connected to this common crankshaft. Okay. And this crankshaft is rotating in this direction. So, radial engine 1 crank shaft, okay, and that is common to all cylinders, and this particular engines, radial engines or radial engine used mostly in early aero engines, this type of arrangements. So, this is what we could not discuss in the last class, but today we have discussed that engine can be further classified based on the cylinder arrangement, and we have seen most common type is the inline, then opposed cylinder type, opposed piston type, and finally radial engine. So, with this now let us move to discuss about carburetor. So, if I write or you also can write so CUR, BURE, TOR, this is American English, while this double TOR British. So, today we shall discuss about carburetor. Why this particular element is needed? Of course, for the SI engines. We have discussed that for the SI engines, fuel air are allowed to mix prior to the arrival in the cylinder before combustion, and this particular mixing is carried out by a device which is the carburetor. So, carburetor is a mechanical element or device. The sole purpose of this device is to provide homogeneous mixture of fuel and air to the cylinder depending on the engine requirement. So, this particular device, if I write the function, so allows to mix air and fuel before introducing in the cylinder and produce air fuel or fuel air mixture, air fuel or fuel air mixture, okay, as per the requirement. Okay. You know that whether it is we are calling it fuel air mixture or air fuel, it is same, and this is known as charge for the SI engine. So, essentially to obtain homogeneous charge depending on the requirement of the load or power of the engine, carburetor is needed. So, this is the objective or or function of the carburetor. Now, if we try to draw the schematic, this is top dead center, this is bottom dead center, and this is the fuel path and this is the air path, and this device is carburetor, and we have another component, this is called throttle valve, right. So, adjacent to this particular element, that is carburetor, there is a valve which is called the throttle valve, and we have intake valve, exhaust valve, and of course, we will have spark plug. So, you can see that when piston is at the TDC, both valves are closed, piston is travelling from TDC to BDC, intake valve will open, and there is a pressure difference between the upstream and downstream of the throttle valve. So, this entire part is filled with combustion gases. If we consider a particular cycle, after a particular cycles, after a particular cycle of operation, this space which is the clearance volume is filled with combustion gases, and there is a pressure difference between the upstream and downstream parts of the throttle valve, and that is why this throttle valve is given, because this pressure is relatively higher inside the cylinder, while pressure upstream the throttle valve is also less. Now, when piston is coming from TDC to BDC, intake valve opens and the pressure inside the cylinder reduces, exhaust is remaining closed. When the pressure difference is such that upstream pressure becomes higher than the further downstream pressure of the throttle valve, this fuel air mixture comes from the carburetor into the cylinder, and this carburetor, you can see that the fuel will come from fuel path that would be supplied to this carburetor by a fuel pump or any pressurizing system, while air should be taken from surroundings. Now, if we need to supply air by overcoming the frictional resistance of the flow, because air will flow through a conduit intake manifold. So, there will be frictional losses, and overcoming the frictional losses, if we need to have flow of air. So, pressure inside this or upstream the throttle valve should be even less than the atmospheric pressure. Now, when throttle valve is fully open, then pressure at the upstream and downstream of throttle valve is almost same. Whatever is the case, issue is that throttle valve is also there adjacent to the carburetor, and this throttle valve is provided to control or regulate the flow of air fuel mixture. Air fuel mixture to introduce in the cylinder. So, carburetor will provide homogeneous mixture of fuel air or air fuel mixture, but that mixture, homogeneous mixture will be, what would be the ratio of fuel and air, that would be decided based on the engine load or power, while how much homogeneous charge or air fuel mixture will go into the cylinder, that will be controlled by this throttle valve. So, this is why that is why this valve is there. Okay. Now, as we have mentioned that the sole objective of the carburetor is to provide homogeneous air fuel mixture, right. So, if we write carburetor, so is provided to supply homogeneous mixture of air fuel ratio or fuel air ratio. So, I am writing this abbreviated forms air fuel mixture or fuel air mixture. Now, homogeneous mixture, fuels are hydrocarbon, families of hydrocarbon, right, several hydrocarbons. Now, when we take any particular fuel, that fuel is introduced inside the cylinder and it will be combusted, combustion is needed, and combustion is an exothermic reaction. We will be getting heat in the form of energy in the form of heat, and also we will be getting several components, that is those are the combustion gases. So, that high pressure high temperature is needed. Now, for the combustion we need to supply air, we need to supply air for the combustion, because the oxygen content in the air is needed for the efficient combustion. Now, when you are talking about homogeneous mixture of fuel and air or fuel air mixture or air fuel mixture, we need to ensure that the amount of oxygen needed for the efficient combustion of that particular fuel would be there in the air which is being supplied. So, in a way the carburetors are used to supply chemically correct or stoichiometric air fuel mixture or fuel air mixture, right. Why? Because the amount of air that should be supplied must contain sufficient oxygen which is needed to burn that fuel, that is to ensure that combustion should be efficient. And if we can ensure that, provided if we supply chemically correct amount, that is the stoichiometric. The word stoichiometric I have written over here, that is the chemically correct air fuel ratio. So, now let us talk about what is air fuel or fuel air mixture. Say if we talk about, because I have already introduced air fuel or fuel air mixture. So, now the chemically correct or stoichiometric air fuel or fuel air mixture should be supplied by the carburetor, and the special feature of this particular element is to provide chemically correct air fuel ratio as per the requirement of the engine, and it may vary if load or power required by the engine varies, right. So, this is very important. This particular ratio will vary if engine load varies. Okay. So, now issue is we can see that carburetor is not only used to supply homogeneous mixture of air and fuel, it is also used to supply chemically correct or stoichiometric air fuel mixture even at varying load condition. So, engine when it is running, sometimes it may operate in a given load condition. After that particular period, maybe load demanded by the engine is increased. That time also carburetor would be able to supply chemically correct air fuel ratio. So, now as I have said that air fuel mixture or fuel air mixture, what do you mean by that? What do we mean by air fuel mixture or fuel air mixture? So, now let us write here fuel air ratio. So, this is fuel air ratio. So, this is basically the amount of fuel. So, this particular ratio indicates what is the amount of fuel with respect to 1 kg of air. So, the amount, what is the amount of fuel with respect to 1 kg of air? That is the chemically correct. So, we really do not know what is the amount of fuel needed for that particular condition when the load is constant, and for a given load if we know that this much amount of fuel is needed. So, to burn that fuel, what is the amount of oxygen, what is the amount of air is needed, and that is why this is we need to supply using this carburetor. So, the fuel air ratio is the amount of fuel with respect to 1 kg of air. If it is air fuel ratio, it is reverse, that is the amount of air with respect to 1 kg of fuel. So, fuel air ratio or air fuel ratio that is A by F. So, the definition is this and vice versa. Okay. So, this is we have discussed. Now, let us discuss it taking an example. So, if we take or if we take a particular fuel and if we can write the chemically balanced equation for that particular fuel, and then we can quantify what would be the fuel air ratio or air fuel ratio. So, let us consider let us consider a fuel, and that fuel is C8H18. Okay. So, if this is the fuel, then chemical reaction for the fuel is, suppose this fuel is used for the SI engine and that fuel would be supplied to the engine cylinder through the carburetor, because we need to supply chemically correct or stoichiometric air fuel ratio. So, what would be the chemically correct air fuel ratio for this particular fuel for essentially for the efficient combustion? We need to write the combustion reaction. So, this is this plus O2 and we will be getting CO2 plus water vapor. So, this is the combustion reaction. So, if we need to supply chemically correct, then we need to balance this equation, and if we balance it, we can write like this plus 9 H2O, then we can see 16 plus 9 25. So, it should be 12.5, right. So, this is the balance chemically balanced equation. Now, we can calculate this particular reaction or equation. This gives amount of air needed to burn 1 kg of fuel. So, this is we have written what is the amount of fuel with respect to per kg of air, that is the fuel air ratio. Now, we are trying to find out amount of air that is needed to burn 1 kg of fuel, that is air fuel ratio. So, this is if we write this will give air fuel ratio. Okay. So, what we can do next? So, we know that, so this is kg of O2 per kg of fuel. So, we can calculate that this much kg of fuel, if we need to burn, this much kg of oxygen is needed, and this much kg of oxygen should come from how much kg of air, that we need to calculate. From there we can calculate air fuel ratio, very straightforward and simple. So, you know that kg of O2, that means if we get it. So, this is if I write using, so this is 12.5 into 32, and this is 8 into 12 plus 18 into 1 into 18. So, you can see this is 400 divided by 114, that is 3.509, right. So, that means this is kg of oxygen per kg of fuel we have calculated. Now, so we know if the, let us write here that if we consider 1 kg of air contains 0.23 kg of oxygen, 0.232 kg of O2. So, this is what is given. So, we have calculated by this time the kg of oxygen needed to burn per kg of fuel, and from there if we know that 1 kg of air will having this much kg of oxygen, then we can straightway write kg of air divided by kg of fuel, and that is 3.509 divided by 0.232, right, and this is 15.12. So, basically you can also calculate very simple. Now, so this we can write like this, kg of oxygen per kg of fuel into kg of air by kg of oxygen, right. So, this is what we have obtained is 15.12, and this we can write like this, kg of O2 by kg of fuel into kg of air divided by kg of O2, and this is 1 upon 0.232 because per kg of air contains 0.232 kg of oxygen. So, that is why we have divided by 0.232. So, essentially this is 3.509. This quantity is 3.509 multiplied with 1 upon 0.232, and that is 15.12. So, this is basically air fuel mixture. So, kg of air by kg of fuel, that is air fuel mixture. Okay. So, we have calculated for this particular fuel air fuel mixture equal to 15.12. So, fuel air mixture that is F upon A will be 1 upon 15.12, right. So, this is so these two are obtained from the balance of reaction. Okay. Now, these two are obtained from the balance of reaction. So, for that particular fuel, if we need to supply to the engine cylinder, the chemically correct air fuel ratio should be 15.12 or fuel air ratio should be 1 upon 15.12. Now, it is very unlikely that always this carburetor would be able to supply chemically correct or stoichiometric air fuel ratio. It is very important, and it is also not necessary that always engine needs stoichiometric air fuel ratio. It is not possible even from any mechanical in element or device. So, there must be a specific range of the fuel air ratio or air fuel ratio for which combustion will occur efficiently. So, this particular range is known as combustible range. Let me tell you once again, we could calculate the air fuel ratio or fuel air ratio for this particular fuel, which is C8H18, and that we have calculated from the balance reaction. We had seen that the stoichiometric air fuel ratio is 15.12 or fuel air ratio is 1 upon 15.12. If we need to run at this condition, so carburetor would be able to supply this ratio, but it is very unlikely that any mechanical that a particular mechanical element or component will be able to supply this particular ratio for a long time, and it is also not needed that engine needs stoichiometric air fuel ratio always. Instead, there must be a specific range for which engine would be able to run efficiently following the proper combustion, and that particular specific range is known as combustible range. So, this is combustible range So, this is a range of fuel air ratio or air fuel ratio for which engine should run following efficient combustion. So, this is very important. If so, this is what is very important, that we need to specify what is that particular range, what is the combustible range for this particular fuel, and if carburetor is unable to provide that, or is carburetor is providing a fuel, carburetor is providing fuel air ratio which is beyond, or I mean beyond this particular ratio, then combustion will not occur. So, that means whenever a carburetor is designed, it is designed keeping in mind that it would be able to supply stoichiometric air fuel ratio, but it is a mechanical element, mechanical device. So, it is not, it is very unlikely that this particular element would be able to provide chemically correct air fuel ratio for a longer period of time. What is needed is, we need to specify a range of the air fuel ratio or fuel air ratio for which combustion will occur efficiently and engine should run. If the air fuel ratio is above or below that particular range which is being supplied by the carburetor, then no combustion will occur. So, carburetor would be able to supply fuel air ratio within this particular range instead of supplying fuel air ratio at a stoichiometric condition always, though it is designed to supply stoichiometric air fuel ratio. So, for this particular fuel C8H18, if we try to draw, so this is say, so this is air fuel ratio 15.12. Now, we need to specify the range. So, this is the range, say this is 8 and this is 20, right. So, this is air fuel ratio. When air fuel ratio is, for this particular fuel, it is measured from experimental investigations, that when air fuel ratio is, that is the combustible range of this particular fuel is this. When the air fuel ratio is 8, though it is not stoichiometric, but engine should run. When the air fuel ratio is even above 15.12, we can see when it is above, then more amount of air is present in the mixture, when it is less, then less amount of air is present in the mixture. But so long as the ratio is maintained within this range, then combustion will occur efficiently and engine will run, and this is the combustible range. So, this is the combustible range. If it is above 20, then we can see that the mixture will contain, when air fuel ratio is greater than 20, mixture will contain more air, while the when air fuel ratio is less than 8, mixture will contain less air. So, we can see that means the carburetor will not supply air fuel mixture which is above 20, below 8. If this is the case, then no combustion will occur. If it is having maximum more air, if the mixture contains more air, then combustion will not sustain, because the flame that will produce, the temperature that will produce will be taken by the excess air present in the mixture. So, flame will not sustain. If the mixture contain less air, that means it is having rich in fuel, less air, that is if it is less than 8, then that means the amount of air needed for that particular fuel is not there. So, it is rich in fuel. So, what will happen, that the flame that will produce, that will be absorbed. So, in this case, if it contains more amount of air, that air will carry away the amount of heat being produced because of the combustion, and combustion will not sustain. If this is the case, when less air is present, that is rich with fuel, then combustion will start, temperature will produce, but the produced temperature will be absorbed by the excess amount of fuel present in the mixture, and hence combustion will not sustain. So, in both these two cases, combustion will not sustain and it is not desirable one. So, for any particular fuel, we need to specify the combustible range, and carburetor would be able to supply fuel air ratio or air fuel ratio within this range, though it is designed to supply always stoichiometric air fuel ratio. In fact, engines do not require to get a stoichiometric air fuel ratio always, and that is why this combustible range is identified. So, to summarize today's discussion, we have discussed about the classification of engine based on the cylinder arrangement, then we have discussed about the carburetor, why this particular element is needed for the operation of SI engine, then we have discussed about the functioning of this particular element, and taking an example, we could obtain the stoichiometric air fuel ratio, which is very important for the supply for the efficient operation of the SI engines. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.